Welcome to training on precipitative softening using lime and soda ash. My name is Geneva Vanderberg. I am a district engineer at Eagle, and I'll be talking through this topic with you today. To start us off, precipitative means to bring out of solution and settle by gravity. This is one way we can remove hardness from water. Softening is the removal of hardness from water. Why do we want to remove it? Hardness can be a nuisance problem, like plugging up your shower head, or a major headache, like causing your water heater to fail, or even catastrophic in the case of a nuclear power plant cooling water. Removing hardness is not a health-based treatment. There is no requirement or regulation regarding hardness or calcium and magnesium. Removing hardness is a service provided to the end water user to make the experience more pleasant. How do we soften? There are commonly considered three ways of removing hardness: reverse osmosis, shown on the upper right, is a high-pressure physical separation of hardness from the water. There are a few of these in the state of Michigan, as well as this technology is used frequently in industry. Ion exchange softening is very common in residential settings, with many people on private wells utilizing ion exchange softening. This presentation is going to focus not on those two technologies, but on precipitative softening, which is the most common method of softening a public water supply. The photo here of a test tube shows what happens when lime is added to water, causing precipitation of hardness. What is hardness? How do we define it? Hardness is primarily the sum of divalent cations, which is typically calcium and magnesium. Calcium and magnesium are both positively charged ions, or what we call cations. They want to bond with negatively charged ions, or anions. Opposites attract, the positive and the negative. There are two types of hardness we are going to talk about: carbonate hardness and non-carbonate hardness. Carbonate hardness is the calcium and magnesium that is associated with carbonate and bicarbonate. Non-carbonate hardness is the calcium and magnesium associated with any other anion. We will continue to cover this concept throughout the presentation, so just remember that hardness is how much calcium and magnesium is in the water, and the type of hardness is determined by which negatively charged anions are in the water. When talking about hardness and softening, how do we define what is too hard or too soft? Here is a typical scale. We define water as extremely hard when the concentration is above 300 milligrams per liter. Much of mid-Michigan groundwater is in this range. Most softening plants leave the water moderately hard, between 75 and 150 milligrams per liter. Speaking of milligrams per liter, what are these units exactly that we're seeing? Remember that hardness is the sum of calcium and magnesium, but we can't just add those together. Think of it like this. If I have 10 pesos and 10 euros, can I just add those together to get $20? No. I have to convert the pesos to dollars, then convert the euros to dollars, then I can add the dollars together. The same is true of the units here. I cannot add milligrams per liter of calcium to milligrams per liter of magnesium. I have to convert them both to a common unit, like dollars. So in the industry, we use a unit called milligrams per liter as calcium carbonate. We will talk more about this throughout the presentation. Sometimes we use words and sometimes we use symbols for different compounds in water. This slide gives a quick reference of the names and chemical formulas for different compounds we see frequently in softening. These chemical formulas are important for calculating the molecular weights, which is how we do that converting from pesos to dollars or from calcium to calcium carbonate. What chemicals do we use in softening? Hydrated lime, made from quicklime, is used to remove magnesium hardness and calcium carbonate hardness. It typically increases alkalinity when added, but all that alkalinity is then removed, leaving water with low alkalinity. Soda ash is used to remove calcium non-carbonate hardness, which isn't removed from lime. It is important to remember this designation of which chemical removes what when you're doing your calculations, so make a note. Additionally, caustic soda is sometimes used for softening, but we are not going to go into detail with that today. Shown here are a variety of surface water treatment systems in Michigan. Some of these use Lake Michigan water, while others use groundwater under the direct influence of surface water. So you can see the hardness from Lake Michigan is much, much lower than that from groundwater, as well as the alkalinity. If we look at the water cycle, it makes sense that hardness would be higher in groundwater than it is in surface water. In the ground, the movement of water is slowed way down, allowing a lot of contact time with the minerals that are naturally occurring in the ground. In Michigan, we have a lot of limestone and calcium in the ground, which gets easily dissolved into the groundwater, increasing hardness. While surface water is greatly diluted between groundwater recharge as well as other surface waters, runoff, and rainfall, so the hardness is typically lower. Let's get back into the discussion of units. When do we use which unit? Starting with milligrams per liter, this is used when describing the concentration of a single compound or element, calcium for example. Milligrams per liter as calcium carbonate is a common unit that we convert other units to when we need them to interact, determining total hardness from calcium and magnesium, for example. Millit equivalents per liter is another form of common unit that can be used, but we aren't going to talk about it here. Grains per gallon is also a common unit that you usually see in residential softening applications. Today, we will be sticking to milligrams per liter and milligrams per liter as calcium carbonate. In addition to hardness, alkalinity is a key factor in the softening process. What is alkalinity? It is the sum of hydroxides, carbonates, and bicarbonates in a common unit, typically milligrams per liter as calcium carbonate. Alkalinity is the ability to neutralize acid, so it is important when making adjustments to pH like we do in softening. Recall that positive and negative ions in water will bond, and how and which ions bond is specific to the individual water. So, calcium and magnesium, which are the hardness cations, will bond with negative ions. When calcium and magnesium bond with carbonate, bicarbonate, or hydroxide, that is considered carbonate hardness. Calcium and magnesium can also bond with other anions, such as chloride, sulfate, or nitrate, and that is what we call non-carbonate hardness. This is a key concept, so we will continue to talk about it throughout this presentation. If alkalinity can be carbonate, bicarbonate, or hydroxide, how do we know which it is? Alkalinity is pH dependent, so the form of alkalinity will change based on the pH of the water. At a high pH, which is a basic water, alkalinity will be in the hydroxide form. As pH is decreased, adding more acid, alkalinity moves to carbonate and then to bicarbonate. During softening, we are adjusting the pH, so we'll move through different forms of alkalinity. Solubility is another important concept of softening. Solubility is how much of something can be dissolved in water. If you add salt to a cup of water, you will keep adding salt and stirring, and the salt will dissolve. But at some point, the salt won't dissolve anymore, and you'll get a pile of salt in the bottom of the glass. If I take that same water and boil it, I will have salty water and a pile of salt on the bottom of my pan, because the solubility of salt is not very dependent on temperature. But if I do this same experiment with sugar, add sugar to a glass of water, I can keep adding sugar until eventually the sugar is piled up on the bottom of the glass. If I boil that sugar water, all the sugar will dissolve, just like making candy or fudge. The solubility of sugar is very dependent on temperature, so more sugar can be dissolved in hot water than in cold water. Solubility in general is also dependent on pH. If I want to remove calcium from water, I can add more calcium, increasing the pH and reducing the solubility so that all the calcium I added precipitates out, and even more that's already there in the water also precipitates out. That's how we handle lime softening. We oversaturate the water with calcium so we can precipitate out more calcium. This produces a pretty unstable water, so we will have to deal with that. It also produces a lot of calcium sludge that has to be disposed of. How do we add calcium to the water? Lime, specifically quicklime or calcium oxide. Quicklime is created by heating limestone in a kiln above 1500 degrees Fahrenheit, which drives off the CO2 and makes the lime very reactive. This process is called calcination. Lime is often purchased as pebble quicklime, like what is shown in this picture. After years of purchasing pebble quicklime myself, I have never seen a batch looking so crisp and clean as this photo. If your quicklime looks a bit more banged up than this, that's totally normal. Now we need to take that pebble quicklime from the previous slide and turn it into something we can measure and dose into the water treatment process. That's where this equipment called slakers comes in. On the left photo, there is a conical hopper feeding from a lime silo above, then a gravimetric feeder weighing the quicklime, which then goes into the slaker. The photo on the right is the gravimetric feeder. Inside the slaker is where the magic happens, creating slaked or hydrated lime and removing any impurities like rocks or sands. Hydrated lime is a milky liquid created by mixing quicklime and water. This is an exothermic reaction and produces a lot of heat. The slaker manages this process by getting the correct mixing proportions and allowing time for the reaction, removing impurities like rocks and sand from the mixture, and removing the excess heat from the reaction. There are generally 4 different types of lime slakers on the market. A slurry or detention slaker is the most common in the water industry. They typically operate at a lime to water ratio of about 1 to 4, or sometimes operate based on a temperature set point. This type of slaker has 2 chambers, a mixing chamber, then a grit removal chamber, where cold water is added to allow grit to settle and be removed by a screw auger. Paste slakers are another type of slaker where a thicker paste is formed, which is then typically diluted and the grit removed afterwards. Ball mill slakers are not frequently seen in the water industry. Batch slakers are sometimes used along with an aging tank to produce hydrated lime in batches while also meeting continuous flow demand. Which slaker you use is often operator preference. Slakers need to be adjusted just like any other chemical feed equipment. Sometimes the quicklime that you have is more or less reactive than the previous delivery, or the water going into the slaker is a different temperature for some reason. The flow through the plant changes, so the feed rate needs to change, or the flow could be the same, but a change in raw water hardness would indicate an adjustment needed to the slaker. What can we actually adjust on a slaker? The lime feed rate and the water flow. How this is controlled is dependent on your specific setup. Where does this softening happen? Well, it happens in clarifiers. There are several different types of clarifiers used for softening. Shown here is a solids contact upflow clarifier. Water enters into the bottom of the center mixing zone. Lime is added in this rapid mix zone as well. Water flows up through the center mix zone, down through the slower mixing zone or flocculation zone, then flows underneath the skirt and enters the sludge blanket at the bottom of the clarifier. Flow velocity is reduced as water travels upwards, causing more and more material to precipitate and settle out. There is also a sludge blow-off line that helps control the size of the sludge blanket. Some of that sludge is usually recycled back into the process to seed the reactions. This is another example of an upflow clarifier, with water entering the center mixing zone from the top, along with lime, then flowing down and under the skirt, into the sludge blanket and up into the effluent troughs. There is still a location to draw off sludge from the clarifier. Here is another view of the upflow clarifier. You can see the green center mixing tube and the dark blue skirt that water flows under. Here, you can also see the sludge scrapers on the bottom used to collect the sludge. The water flows up into the launder system at the top. This is a photo looking down into an empty clarifier, where the green is the skirt, and you can see the water laundering weir at the top. Equipment associated with lime softening easily gets caked with calcium carbonate and requires annual maintenance, as you see here. A claricone is a different type of clarifier used in water softening. It features an adjustable overflow slurry concentrator. Mixing occurs with eccentrically loaded inlets that cause a swirling action as water rises from the bottom. As water flows upwards, hardness precipitates out. The adjustable cone allows adjustment of the sludge blanket. If the sludge blanket rises too high, it will carry over into the outlet and onto the filters, causing a lot of filtration issues. Here are a couple photos of claricones at Mount Pleasant. A more traditional flocculation sedimentation basin setup can also be used for lime softening, as shown here. Water flows into a rapid mix chamber where chemical is added, then into flocculation chambers with slow mixing paddles, and finally into a sedimentation chamber where sludge is settled out and scraped off the bottom. Now we're going to get into the fun stuff. We have already covered that total hardness is the sum of calcium and magnesium in consistent units. We have also talked about carbonate hardness and non-carbonate hardness. As a refresher, carbonate hardness is hardness that is associated with carbonate or bicarbonate. Non-carbonate hardness is hardness associated with other anions like sulfate or chloride. This diagram shows how you can end up with 4 possible types of hardness: calcium carbonate hardness, calcium non-carbonate hardness, magnesium carbonate hardness, and magnesium non-carbonate hardness. It is important to understand which of the 4 types of hardness is in the water and in what quantities. This is how we determine chemical dosing for softening. We use lime to remove calcium carbonate hardness, magnesium carbonate hardness, and magnesium non-carbonate hardness. That is 3 out of the 4 types of hardness. Calcium non-carbonate hardness cannot be removed with lime. A little wrinkle in this is that removal of magnesium non-carbonate hardness with lime actually creates additional calcium non-carbonate hardness, which cannot be removed with lime. It is always the non-carbonate hardness that is more difficult to manage. We use soda ash to remove calcium non-carbonate hardness. I'm going to keep discussing this in different ways so you will understand the concepts and be able to apply them to your softening calculations. Here's a little practical cheat sheet to keep in mind. If your non-carbonate hardness is low, you can generally soften with just lime. Remember that lime removes calcium carbonate hardness and magnesium carbonate hardness. Also remember that removal of magnesium non-carbonate hardness with lime will actually create calcium non-carbonate hardness that will require soda ash to be used. If your water has a higher level of non-carbonate hardness, you will need to use soda ash to remove it. If you are only removing calcium hardness and not magnesium, pH operating range is 10.3 to 10.6. But for magnesium removal, the pH needs to be much higher, above 11. We recommend that any magnesium hardness above 40 milligrams per liter as calcium carbonate be removed to prevent magnesium hydroxide scaling on water heaters and boilers. These are the chemical equations that illustrate everything we just learned. Something we really haven't touched on yet is carbon dioxide. Water typically has some level of CO2, which will react with the lime we add to the water. So the first equation here shows the removal of carbon dioxide from the water. CO2 reacts with hydrated lime to create calcium carbonate and water. Note that the calcium carbonate in this first equation has a down arrow next to it. That arrow represents a precipitate, which means that calcium carbonate in this equation is a solid and can settle out of the water. The next equation is the removal of calcium carbonate hardness. Calcium bicarbonate reacts with hydrated lime to produce calcium carbonate precipitate and water. The third equation shown is the removal of magnesium carbonate hardness, where magnesium bicarbonate reacts with hydrated lime to produce calcium carbonate precipitate and magnesium carbonate. The fourth equation takes that magnesium carbonate that we just produced, reacting with hydrated lime to produce calcium carbonate and magnesium hydroxide precipitate. Remember that in these chemical equations, anything with a down arrow or an S in parentheses is a solid and has to be disposed of as sludge. In the last slide, we talked about removal of carbonate hardness with lime. Now let's talk about non-carbonate hardness. Equation 5 shows us that calcium non-carbonate hardness, or in this case, calcium sulfate, reacts with soda ash to create calcium carbonate precipitate and sodium sulfate. In equation 6, we see that magnesium non-carbonate hardness, or magnesium sulfate here, reacts with hydrated lime to create magnesium hydroxide precipitate and calcium non-carbonate hardness, as calcium sulfate here. That additional calcium sulfate would need to be removed with soda ash, as shown in equation 5. We will be applying these concepts and equations directly to calculate lime and soda ash dosing. Recall that the pH during softening is pretty high, at least 10.3 and sometimes over 11. The water is also unstable, oversaturated with calcium, and can cause calcium deposition on weirs, pumps, pipes, etc. So we want to stabilize that water once we have the total hardness where we want it. Also recall that the first reaction of softening was lime reacting with naturally occurring carbon dioxide in the water. Now, at the end of the process, we want to add in some additional carbon dioxide to react with the excess lime or calcium to turn it back into a soluble form that will stay in solution instead of plating out on our pipes. We also add carbon dioxide to reduce the final pH of the water. The source of carbon dioxide can be purchased CO2 from a chemical supplier or CO2 naturally occurring in the water by utilizing split treatment, which we'll talk about later. This whole process is called recarbonation. We have thrown a lot of chemistry at you, so we're going to take a quick chemistry break, but don't worry, it will come back. All that hardness we removed, the calcium carbonate hardness, calcium non-carbonate hardness, magnesium carbonate hardness, and magnesium non-carbonate hardness, all has to go somewhere. We take it out of the water, but then where does it go? It is sludge. The sludge helps to seed the softening reactions, but most of it does need to be disposed of. The primary components of the sludge are dependent on the source water, but usually just calcium carbonate like wet chalk and magnesium hydroxide. We showed 6 different chemical equations for softening, but in reality, these happen together in various treatment configurations. There are 3 main types of configurations for softening: single stage, 2-stage, and split treatment. There are a lot of variations of what I'm going to show you in the next few slides, so don't worry if the water plant you operate doesn't fit neatly into one of these categories. This is a diagram of a single stage lime softening setup. It looks complicated, but let's walk through it step by step, starting on the left. Raw water comes in, typically from a groundwater source, and enters the primary treatment basin or clarifier. Hydrated lime slurry is added into the same treatment clarifier. This clarifier would be like one of the several different types we went over earlier in the presentation. Our lime softening reactions take place within the clarifier. Precipitate is formed and settles to the bottom. Sludge is removed, with some being recycled back into the treatment basin. Treated or softened water then flows into a recarbonation basin where CO2 is added. In this case, the CO2 would be from a chemical supplier or generated on site. In the recarbonation basin, some settling of solids continues, so those solids have to be removed also. Softened and recarbonated water then flows into a granular media filter. After the filter, that water is softened, stable, and ready for the customer.
Softening can also be done in a 2-stage treatment. This method is more robust and flexible, allowing for use of soda ash and magnesium removal with excess lime. Looking at the diagram, raw water enters on the left where lime is added in the primary treatment. This diagram shows excess lime being added at this stage, allowing for magnesium removal at the higher pH of 11.3. Calcium and magnesium hardness precipitate out and settle to the bottom, forming sludge. Sludge is removed, with some being recycled back into the process to seed the reaction. After this first stage comes recarbonation with CO2. Then water flows into the secondary treatment clarifier, where soda ash is added to remove calcium non-carbonate hardness. Sludge is formed and removed and can also be recycled into the process. CO2 is again added for recarbonation before water is filtered. Another configuration of softening is called split treatment. In this method, we utilize the CO2 in the raw water for the first stage recarbonation. Similar to the other configurations, raw water enters the primary treatment clarifier where lime is added. Hardness precipitates out and settles as sludge. The sludge is removed, with some being recycled back into the process. What is different is that some of the raw water bypasses the primary treatment and is reintroduced downstream, recarbonating that high pH water with the naturally present CO2 in the raw water. The rest of the treatment proceeds the same as the previous slide, with soda ash being added in the secondary treatment clarifier to remove calcium non-carbonate hardness, followed by recarbonation with CO2, then filtration. These are just a few examples, and actual treatment plants will have various combinations of these different examples presented. How do we know where in the process we are when working at an actual softening facility? In a single-stage lime softening process, where we are only removing calcium carbonate hardness, pH can be used to make operational adjustments. You can see that the raw water comes into the plant with a pH of about 7.5. Lime is added and the pH rises to about 10.5 and stays that high until recarbonation brings the pH back down to somewhere in between. This is a simplified version of events, and water plants typically don't use only pH for process control. Let's look at a more complicated 2-stage split treatment softening process. There's a lot going on here that could impact pH. The main flow stream starts with raw water with a pH around 7.5. We add lime and excess lime for magnesium removal in the primary treatment, bringing the pH up to 11.3 in the primary clarifier. Also being introduced into this clarifier is sludge recycle, which can impact pH. Water flows out of the primary clarifier where the bypass raw water is added for recarbonation, which then lowers the pH. But then soda ash is added and some recycled sludge to increase the pH again. After secondary treatment, CO2 is added, lowering the pH. So if we just measured pH, we might not know which part of the process we are in since it goes up and down a few times. A better indicator for process control in this case would be alkalinity. What are some other things that impact the control of the process? Energy does. The rapid mix energy, flocculation energy, and detention time all impact how well the softening and settling process works. Generally, the energy requirements for softening are less than that of standard coagulation, but the detention times are greater for softening. Temperature also impacts how fast and how complete the softening reactions are. Warmer water produces faster and more thorough reactions. Colder water requires more chemical addition for the same results. Instead of pH, we want to use alkalinity to measure each step in the softening process. During softening, we are often operating at elevated pH ranges where alkalinity can change forms easily. Lime softening plants are typically doing alkalinity titrations every shift or multiple times per shift to ensure a smooth process. These measurements are especially important when well combinations are changed, the flow rate is changed, source water temperature is changed, or a new batch of chemicals is being used. How do we titrate for alkalinity? We add acid to a sample of our process water to reduce the pH to a certain endpoint, indicated by a color change. P alkalinity is associated with a pH of 8.3 and is named for the indicator, phenolphthalein. Total alkalinity is associated with a pH of 4.5, using the indicator methyl orange. These are the two endpoints when titrating and indicate a change from one type of alkalinity to another. Use these equations to calculate the P alkalinity and total alkalinity from titrations. If you're here preparing for a certification exam, these equations are given to you on the exam. P alkalinity is calculated as the titrant volume, how much acid did you use to reach the phenolphthalein color change, times the acid normality, which is usually given to you, times 50,000, divided by the volume of your sample. Similarly, the total alkalinity is calculated as the titrant volume to reach the methyl orange indicator color change, multiplied by the acid normality and 50,000, and divided by the sample volume. How do I turn P alkalinity and total alkalinity into something meaningful that helps me understand where in the softening process I am? Use the results of your titrations and this chart to calculate the types of alkalinity you have. This chart is provided on the certification exams, so you don't need to memorize it. Let's take a small break from chemistry and talk about troubleshooting. What are some of the things that can go wrong in a softening plant? Upon startup of the system, sometimes it is difficult to establish a sludge blanket. The sludge blanket is important because it helps with the softening reaction and traps those hardness particles so they settle out of the water. This is why some sludge is often recycled back into the process. Another issue can be bridging in the lime storage bins. Moisture gets into the storage bins, causing the lime to stick together and stick to the sides of the bins, not allowing smooth flow of lime out of the silo. This can be a messy and dangerous problem. The solid lime needs to be transported from the lime bins or silos into the slaker, usually by a belt or auger. These pieces can break down, causing frequent maintenance needs. And then once the lime is slaked or hydrated, the lines that convey the slurry often become caked with lime and easily get plugged, requiring frequent maintenance. One process issue that you can run into is a high pH at the softening clarifier effluent. This could be a failure of the recarbonation equipment or other process control issues. Why does this matter? The water is highly saturated with calcium carbonate, and at the high pH needed for softening, that extra calcium will come out of solution in your pipes, on the filter media, in storage tanks, and in the distribution system. creating a lot of expensive problems. It is important to make sure the water leaving the treatment process is stable. This calcium plating can cause buildup on the filter media, reducing its effectiveness. It can also cause high turbidity readings. Turbidity is often used as a surrogate for pathogens, but this is difficult in a lime softening plant, since often cloudy water is due to lime sludge carryover and not naturally occurring turbidity. Because of this, regulations allow turbidity samples for lime softening plants to be acidized if they show high readings at the compliance location. Now the fun stuff. Calculations. Softening is some science and a lot of art. So all of the calculations we will walk through are just to get you to a theoretical starting point. Field adjustments will be required to reach optimum chemical dosing. Alkalinity titrations will be the best guide for adjusting dosages during plant operation. There are a lot of different ways to calculate theoretical softening dosages, and I'm going to walk you through the simplest version. If you're studying for a certification exam, this is the method and equations that are given on the exam. First, some reminder rules of thumb. These are important, so make sure you understand and memorize them. First, lime removes magnesium hardness and calcium carbonate hardness. Lime cannot remove calcium non-carbonate hardness. Second, when you remove magnesium non-carbonate hardness with lime, you are actually creating calcium non-carbonate hardness that cannot be removed with lime. Third, soda ash is needed to remove calcium non-carbonate hardness. So in order to calculate the doses of lime and soda ash, we need to know what kinds of hardness we have. A note about excess lime before we jump into the calculations. Recall that we need to add excess lime to increase the pH to 11.3 for removal of magnesium. A problem statement on the exam will indicate if you need excess lime and how much. Remember, the lime dose calculations just give us a starting point to operate from and are not exact when we are talking about actual treatment plant operation. Remember, when we do softening calculations, we are talking about a lot of different compounds. We can't just add together the concentrations of these compounds because they are in different units. Just like we can't add 10 pesos to 10 euros without converting them both to the same units. We want to always convert our units to milligrams per liter as calcium carbonate, as is shown here. Think of this as a ratio, just like converting pesos to dollars. There is another common unit called millit equivalents per liter, but we are not going to get into that today. Write these steps down. We will use them on all of our calculations. When solving problems for a question that asks how much lime and soda ash are needed, we always start by making sure all our units work together. So step 1, convert all the units to milligrams per liter as calcium carbonate. Step 2, make sure you know how much total hardness, carbonate hardness, and non-carbonate hardness you have in milligrams per liter as calcium carbonate. Remember that total hardness equals carbonate hardness plus non-carbonate hardness. Step 3 is to make a bar graph, which shows calcium, magnesium, carbonate hardness, and non-carbonate hardness, all in milligrams per liter as calcium carbonate. We will go through this step in detail next. Step 4 is to understand the treatment goal, which is often given in the problem statement. Make sure the units are in milligrams per liter as calcium carbonate. Step 5 is to do our calculations. And finally, step 6 is to account for any excess chemical or impurity of chemical. This bar graph is so important and the key to solving softening calculations. We have our cations on the top and our anions on the bottom. Our cations are always going to be calcium and magnesium. We can generally ignore any other cations. Our anions are always going to be bicarbonate and some other negatively charged ion. In these examples, we assume it is always sulfate. When we build this bar chart, we draw it to scale using common units. If we want to read the bar chart, we start on the left. Recall that total hardness is both the sum of calcium and magnesium cations and the sum of carbonate hardness and non-carbonate hardness. What kind of hardness do we have here specifically? First, we have CO2, which isn't hardness, but it does use up lime, so we include it. Next, we have calcium carbonate hardness. Remember, this is the calcium that is associated with bicarbonate. We also have calcium that is associated with sulfate. This is the calcium non-carbonate hardness. Remember that calcium non-carbonate hardness needs soda ash for removal. Then finally we have our magnesium, which in this case is all associated with sulfate, so is all magnesium non-carbonate hardness. This same bar graph can be created with milli equivalents per liter, but we are going to keep using milligrams per liter as calcium carbonate. Remember that all units need to be converted to the same thing. We can't add pesos to euros. And remember to draw these boxes relatively to scale. Then we can use this chart to determine how much lime and soda ash are needed to reach a certain treatment goal with a given raw water quality. Oftentimes, we don't remove all of the hardness in the water. Usually the problem statement will tell you the treatment goal, or how much hardness to leave in the water. On this slide, start on the left, we want to remove all of the CO2, all of the calcium carbonate hardness, all of the calcium non-carbonate hardness, and some of the magnesium non-carbonate hardness. Let's put some numbers on this process. Here we are given some raw water parameters. We have our CO2, calcium, magnesium, and bicarbonate. This problem is also giving us a hint that we need to calculate the non-carbonate hardness. Let's think back to our previous slide where we gave the steps to solve a softening problem. Step 1 was to convert all the units to something similar. I cannot add calcium and magnesium here to get total hardness. First, I have to convert. So now you see this table with all of the units converted to milligrams per liter as calcium carbonate. Step 2 is to fill in any gaps, like the non-carbonate hardness in this problem. We know that total hardness is equal to the calcium plus magnesium in common units. So we already converted everything to milligrams per liter as calcium carbonate. So now we can add together our calcium of 225 milligrams per liter as calcium carbonate to our magnesium of 61.7 milligrams per liter as calcium carbonate to get a total hardness of 286.7 milligrams per liter as calcium carbonate. We also know that total hardness equals carbonate hardness plus non-carbonate hardness. If we rearrange that equation, we can solve for non-carbonate hardness by subtracting our carbonate hardness from the total hardness we just calculated. So 286.7 milligrams per liter as calcium carbonate total hardness minus our bicarbonate of 260 milligrams per liter as calcium carbonate gives us a non-carbonate hardness of 26.7 milligrams per liter as calcium carbonate. Now let's put that on our bar chart. Note that we have our CO2 on the left, then calcium carbonate hardness, magnesium carbonate hardness, and finally magnesium non-carbonate hardness. This is a different configuration than the last bar chart we looked at. Pay attention to how the anions and cations line up to understand if the hardness is carbonate or non-carbonate. How do we take that bar chart and calculate our doses? We know what we have in the raw water. Now we need to set our treatment goal. Remember, in an exam problem, your treatment goal will probably be given to you. Here the treatment goal is given as 100 milligrams per liter as calcium carbonate. How do we get our dose? We need to learn the equations. On this slide, first notice that we have CO2, calcium carbonate hardness, calcium non-carbonate hardness, and magnesium non-carbonate hardness. Now you see the chemical equations for each of these types of hardness. From here, we could do a lot of chemistry and unit conversions to come up with our lime and soda ash dose. Or we could use some ratios that were already calculated using that chemistry and unit conversion. It is important to understand where the ratios come from, so it is important to understand the concept of these chemical equations. But when doing the actual math, we will use the shortcut version. Here's the same concept, except our types of hardness are a little different. First, we have our CO2, then our calcium carbonate hardness, magnesium carbonate hardness, and magnesium non-carbonate hardness. And our chemical equations change to accommodate this change in hardness types. Again, we want you to understand these concepts, but we will use a shortcut for the calculations. Here are our shortcut ratio calculations. Finally, you made it. The most important part of this table is knowing how to use it. Let me walk you through it. We are using this table to calculate the lime and soda ash dose to remove a known amount of hardness. The units here are a little tricky, so make sure you pay attention. Please note that this table will be given to you on the certification exam, so you don't need to memorize it. As we move through this table, think about moving from left to right on your bar chart. Use this table together with our bar charts. In the first column, we have our source of demand, that is demand of lime or soda ash to remove the named compound. So first up, we have CO2. Note that the units here for CO2 are milligrams per liter as CO2, not as calcium carbonate. We know that we need lime to neutralize the CO2 since this is the first step on our bar charts we've been looking at. This table tells me that if I take my milligrams per liter of CO2 and multiply it by 1.27, I will get the dose of lime needed in milligrams per liter as calcium oxide or quicklime. I warned you that the units in this table are tricky, so just pay attention and write them down when doing your own calculations. Next is calcium carbonate hardness. Remember on your bar chart, this is the calcium on the top that lines up with the bicarbonate on the bottom in milligrams per liter as calcium carbonate. So we take the concentration of calcium carbonate hardness in milligrams per liter as calcium carbonate that we want to remove and multiply by 0.56 to get our lime dose in milligrams per liter as quicklime. Then we do our magnesium carbonate hardness that we want to remove. In our bar chart, this is the magnesium on the top associated with bicarbonate on the bottom. The concentration of magnesium carbonate hardness that we want to remove multiplied by 1.12 gives us the needed lime dose in milligrams per liter as quicklime. Note that removal of magnesium carbonate hardness takes twice as much lime as removal of calcium carbonate hardness, since it is a two-step chemical reaction. Again, you don't need to memorize the chemical reactions, just understand how they impact the calculations. Next, we move on to magnesium non-carbonate hardness. This is the magnesium on the top of our bar chart at the very right edge associated with sulfate. Recall that removal of magnesium non-carbonate hardness creates calcium non-carbonate hardness, so we technically need both lime and soda ash here. To calculate our lime dose, we multiply the amount of magnesium non-carbonate hardness we want to remove by 0.56 to get our lime dose. Then we multiply that same amount of magnesium non-carbonate hardness we want to remove by 1.06 to get our soda ash dose. Calcium non-carbonate hardness cannot be removed with lime, so we move right to a soda ash calculation. The amount of calcium non-carbonate hardness we want to remove multiplied by 1.06 gives us our soda ash dose in milligrams per liter as soda ash. Almost done. Now we calculate our excess lime and excess soda ash dose with the problem statement given information multiplied by these ratios. Then finally, we add up all the lime dose in milligrams per liter of quicklime to give total lime dose, and we add up all the soda ash dose in milligrams per liter as soda ash to give total soda ash dose. Hooray! Here is a different way to look at what we just went through. Moving from left to right on the bar chart, first we neutralize our CO2 with lime, then remove calcium carbonate hardness with lime. Next, we remove calcium non-carbonate hardness with soda ash, and finally we remove magnesium non-carbonate hardness with lime and soda ash. This is the same concept again, but with a different configuration of hardness. Starting from the left, first we neutralize CO2 with lime, then we remove calcium carbonate hardness with lime. Next, we remove magnesium carbonate hardness with lime. And finally, we remove magnesium non-carbonate hardness with lime and soda ash. These are the same ratios and calculations shown on the table a couple slides ago, just in a different layout. If I bring back this same problem from earlier, now we can actually calculate our chemical doses for softening. It took us 66 slides to get here, so great job for sticking with me. Our hardness target here is 100 milligrams per liter as calcium carbonate. This is how much hardness we want to leave in the water. So how do we know how much to remove? We know we need to neutralize the CO2, and we know that the calculation for that requires that our concentration of CO2 be in milligrams per liter SCO2. So that's what we've shown here. Now we need to know how much hardness to remove. We know our total hardness is the sum of calcium and magnesium in common units, which comes to 286.7 milligrams per liter as calcium carbonate. We calculate the hardness we want to remove as the total hardness minus our target hardness, which gives us 186.7 milligrams per liter as calcium carbonate to remove. We can also see in our bar chart that after we neutralize CO2, all the hardness we are taking out of the water is calcium carbonate hardness. Time to plug and chug. Our CO2 concentration of 8.8 milligrams per liter SCO2 times our given ratio of 1.27 gives a lime dose of 11.18 milligrams per liter as quicklime. No soda ash is needed for CO2. We calculated our calcium carbonate hardness to remove on the previous slide as 186.7 milligrams per liter as calcium carbonate. We multiply this by our given ratio of 0.56 to get a lime dose of 104.55 milligrams per liter as quicklime. We don't need soda ash here. No requirements for excess lime or soda ash or for a different purity of chemical were given, so we assume we don't need to worry about that. Finally, we add up all our lime doses in consistent units to get us a final dose of 115.73 milligrams per liter as quicklime. Another very common question is how much lime in pounds is used in a day given a certain flow rate. Let's use the example we just went through. We know our lime dose is 115.73 milligrams per liter as quicklime. Our problem statement asks us how many pounds per day given a water flow rate of 10 million gallons per day. We know the pounds formula from all of our other chemical feed calculations, and we can use that here. We use our concentration times our flow rate of 10 mgd times our factor of 8.34 to get 9,652 pounds of quicklime per day. We have done a lot of work. We calculated our dose of lime to remove the amount of hardness that we want. Is that it? Sorry, no. We can't send water out the door at a pH of 10 or 11. That would lead to pipes being coated in calcium and clogging, hot water heater failure, and potential increased corrosion of copper. Our disinfectant is also not very powerful at that high of a pH. We need to stabilize, and we do this with recarbonation. We recarbonate by adding CO2 to the water, which is saturated with calcium carbonate. We can do this with pure CO2, or we can use split treatment to take advantage of some of the naturally occurring CO2 in the raw water. The Langelier index utilizes finished water parameters, including pH, alkalinity, temperature, total dissolved solids, and calcium, to give an idea of how stable the water is. AWWA has an online calculator to utilize. If the Langelier saturation index is greater than 0, it is considered oversaturated with calcium and will deposit calcium onto pipes and other surfaces. If the Langelier index is less than 0, the water is undersaturated and will tend to be corrosive. Now that we removed unwanted hardness from the water, we still need to deal with it. The hardness comes out of solution and forms sludge. Sludge is removed typically using mechanical mechanisms as part of the clarifier. Often, some of the sludge is recycled to help seed softening reactions. Addition of coagulant can be helpful to manage the sludge removal process. When we remove the sludge, it is still pretty full of extra water. Now we have another problem of dewatering the sludge. This is often done in sludge ponds or lagoons where we use evaporation to pull water out of the sludge. Once it is dewatered, it can be hauled off-site for final disposal. Disposal of sludge can be very costly. The sludge is often beneficially reused in land application for soil pH adjustment in agriculture and sometimes as a soil amendment in construction. Here's an example of what a dry sludge pond can look like. And here's a photo of a sludge pond or lagoon currently in use. To wrap us up, I am going to do one more example problem. There will also be a separate video with more example problems, so be sure to look for that. The following water will be softened to 100 milligrams per liter as calcium carbonate. What dose of lime and or soda ash are required? Assume 90% lime purity and 95% soda ash purity. Assume 25 milligrams per liter as calcium carbonate of excess lime and soda ash each. Alright, there is a lot going on here. Let's go back to using our steps and walking slowly through the problem. Step 1 is to make sure all our units are in milligrams per liter as calcium carbonate. I can see that magnesium and CO2 are not, so we will need to convert those. Step 2 is to calculate total hardness, carbonate hardness, and non-carbonate hardness, and any other unknowns. We are given total hardness and carbonate hardness in the correct units. We can subtract the carbonate hardness from the total hardness to get the non-carbonate hardness. We don't know calcium, so we'll need to calculate it. We know that total hardness is calcium plus magnesium, and we are given total hardness and magnesium, so we just need to subtract to get calcium. But make sure your units are right. Then step 3 is to make our bar graph. Let's get into it. For step 1, we convert the units all to milligrams per liter as calcium carbonate. Remember, we can't add pesos and euros together to get dollars. We have to convert pesos to dollars, then convert euros to dollars, and then we can add them together. The same is true for our units here. Recall from the previous slide that we need to convert CO2 and magnesium. For CO2, we are given a concentration of 15 milligrams per liter as CO2. We multiply this by a ratio of molecular weights to convert to the right units, just like we would do for our pesos example. So 15 milligrams per liter multiplied by 100, which is the molecular weight of calcium carbonate, divided by 44, which is the molecular weight of CO2. Note that the units we want, milligrams per liter as calcium carbonate, are on top of this ratio. That math gives us 34.1 milligrams per liter as calcium carbonate of CO2 in the raw water. We also recall from the previous slide that we need to convert magnesium to the correct units. Following the same approach, we take the raw water magnesium concentration of 10 milligrams per liter as magnesium and multiply it by the ratio of molecular weights to get 41.2 milligrams per liter as calcium carbonate of magnesium. We know calcium to be the total hardness minus magnesium, so here that would be 275 milligrams per liter total hardness minus 41.2 milligrams per liter of magnesium, all in the same units of milligrams per liter as calcium carbonate. Doing this math gives a calcium concentration of 233.8 milligrams per liter as calcium carbonate. And our final unknown is non-carbonate hardness. We are given the total hardness and the carbonate hardness all in the same units, so we just subtract and get a non-carbonate hardness of 115 milligrams per liter as calcium carbonate. Note that in this table, carbonate hardness is represented by bicarbonate and non-carbonate hardness is represented by sulfate, which is what we will show on the bar chart in the next step. This step is where you will need to draw this bar chart to scale on your own based on the concentrations in the previous slides. The numbers here are all in units of milligrams per liter as calcium carbonate. We draw the boxes from left to right, starting with CO2. Then we draw the calcium box and magnesium box, and below those we draw the bicarbonate and the sulfate. It is okay if the top and bottom don't add up to the same total. Remember, this is an estimate of chemical doses, a starting point. The important thing with the boxes is to make sure they are relatively to scale. In this example, calcium is larger than bicarbonate, so that box needs to be longer. This is important because it tells us which type of hardness we have and therefore which chemical we need to remove it. Once we draw the boxes to scale, now it is time to put the treatment goal on here. Remember, the treatment goal is the hardness we are leaving in the water, so we measure this from the right side of the graph. Here you can see the treatment goal line is 100 milligrams per liter as calcium carbonate from the right, which is just slightly less than the 115 milligrams per liter of sulfate. Again, this scaling is important. What do we need to remove to meet our treatment goal? We need to neutralize all the CO2, then we need to remove all of the calcium carbonate hardness, which in this case is equal to the bicarbonate. Then we need to remove a portion of the calcium non-carbonate hardness, which we can do some quick subtraction to figure out. After you have done all this work, now is a good time to check in with the original problem statement to make sure you're still on track to solving the right problem. So, recall that the problem statement asks us to determine the lime and soda ash doses and gives us excess lime and soda ash as well as purity requirements. Let's do the math, and remember to be careful of your units here. First, we calculate the lime required to neutralize the CO2. Remember the ratio given in the chart on the exam requires the CO2 concentration to be in milligrams per liter as CO2. So we have 15 milligrams per liter times the ratio of 1.27 gives us a lime dose of 19 milligrams per liter as calcium oxide or quicklime. Next, we calculate the lime dose needed to remove the calcium carbonate hardness. We take the concentration of calcium carbonate hardness to remove, which we calculated on the previous slide as 160 milligrams per liter as calcium carbonate, multiplied by the given ratio to get a lime dose of 89.6 milligrams per liter as quicklime. We also had 15 milligrams per liter as calcium carbonate of calcium non-carbonate hardness to remove. Remember that we can't remove calcium non-carbonate hardness with lime, so we need to use soda ash here. So 15 milligrams per liter as calcium carbonate times the soda ash ratio gives us a soda ash dose of 15.9 milligrams per liter as soda ash. Can we add these doses together now? No. Our problem statement called for excess lime, excess soda ash, and impurities in both chemicals, so now we need to calculate those. We were given the excess lime dose of 25 milligrams per liter as calcium carbonate, So we multiply this by our given ratio to get a lime dose of 14 milligrams per liter as quicklime. Similarly, for soda ash, we were given an excess dose of 25 milligrams per liter as calcium carbonate, so we multiply by the ratio for soda ash to get an excess soda ash dose of 26.5 milligrams per liter as soda ash. Let's add up our lime dose and soda ash doses separately. For lime, we have 19 plus 89.6 plus 14, which gives us a total of 122.6 milligrams per liter as quicklime. For soda ash, we add up 15.9 and 26.5 to get 42.4 milligrams per liter as soda ash. Are we done now? Sorry, no. Our problem statement said that our lime was 90% pure and our soda ash was 95% pure. Let's think about that for a minute. If our lime is less than 100% pure, does that mean we are going to need more or less lime? More. So in doing this calculation, use that as a final gut check. Let's take our calculated lime dose of 122.6 and divide by 0.9 or 90% to get a final lime dose of 163.2 milligrams per liter as quicklime. And for soda ash, we take our calculated dose of 42.4 and divide by 0.95 or 95% to get a final soda ash dose of 44.6 milligrams per liter as soda ash. Our quick gut check shows us that these final doses are higher than if the chemical was pure, so we know we did that final bit of math correctly. That was a lot of information today, and you did great. Keep practicing, and you will be a softening pro in no time. Look for my other video with lots of example problems. Thank you.